Now let us go to the Nusselt number correlations for flows within parallel plate channels. Before we go further, you may ask, why do we need to study this? This topic is actually very important when we want to compute for the convection heat transfer coefficients in finned heat sinks in heat exchangers and in arrays of printed circuit boards within our electrical or electronic equipment. Now that you know the importance of learning this topic, we can now proceed with our discussion. Let us first discuss the Nusselt number correlation for flows within isothermal parallel plate channels such as fins. First, it must be noted that for fin surfaces, the characteristic length corresponds to the fin spacing. Therefore, the Rayleigh number in this case can be computed using this formula. Finally, this is the Nusselt number for isothermal parallel plate channels recommended by Bar-Cohen and Rosenoff. One interesting question that is always raised when we talk about heat transfer from finned surfaces is what should be the optimum fin spacing that can maximize the rate of heat transfer from the finned surface. Before we answer this, let us first look at the benefits and drawbacks of having closely spaced fins and widely spaced fins. The main advantage of having closely spaced fins is that there is a higher fin surface area from which convection heat transfer can occur. But since airflow between these fins are somehow restricted, the convection heat transfer coefficient within this fin arrangement is quite low. Now let's go to widely spaced fins. Since there is a wide area within which air can flow in widely spaced fins, then we can expect that the convection heat transfer coefficient will be high. However, this is counteracted by the lower fin surface area where convection heat transfer can occur. Now, how do we find the optimum fin spacing that can provide a balance between these two factors? It has been experimentally determined that the optimum fin spacing of very thin fins can be computed using either of these two correlations. Take note that when computing this Rayleigh number, the characteristic length that must be used is the fin spacing, while when computing this Rayleigh number, the characteristic length that must be used is the fin width. Now, it has also been determined experimentally that if we use the optimum fin spacing in the computation for the Nusselt number will remain constant at 1.307. Finally, when we want to compute for the rate of natural convection from isothermal fins, we can use this formula derived from Newton's law of convection. Take note that n in this formula corresponds to the number of fins on the surface, and it can be computed by dividing the entire length of the fin surface by the sum of the fin spacing and the fin thickness. On the other hand, L and H in the formula correspond to the fin width and the fin length, respectively. Now let us discuss how we can compute for the Nusselt number for convection heat transfer occurring within channels of vertical parallel plates that emit a constant heat flux. Examples of these surfaces are printed circuit boards that are commonly found in electronic equipment. This is the formula for the Rayleigh number under this case. Q sub S over dot corresponds to the constant surface heat flux emitted by each plate, while these fluid particles must be evaluated based on the average of the temperature at the upper edge of the plate T sub L and the temperature of the fluid surrounding these surfaces T sub infinity. Take note that for Isoflux vertical surfaces, the maximum temperature on these surfaces can be found at the upper edge since, as we all know, This is the last point at which the cooling air coming from the bottom will flow over. Finally, this is the correlation recommended by Bar-Cohen and Rosenov to compute for the Nusselt number under this case. We can find the value of the maximum surface temperature at the upper edge of the Isoflux vertical surface using this formula. On the other hand, the optimum spacing of the Isoflux vertical plates that will allow the highest rate of heat transfer is given by this formula. Finally, the total rate of heat transfer from this constant heat flux vertical parallel plates is given by this formula. Again, take note that N corresponds to the number of parallel plates, and it can be computed by dividing the entire length of the base surface where these plates are attached by the sum of their spacing and thickness. In the next video, we will discuss the Nusselt number correlations for flows within enclosures.